So I'm going to talk about random graphs with specified degree sequences, and a few speakers this morning have talked about this probability space, and it's a hard one. It's basically quite hard to analyze, and the goal of this talk is to just show how we can make our life a little bit easier if you have to treat these random graphs. So the talk is based on some collaborations with Isaac, Mckay, and Hopkins. So Misha and Brandon, they were here in this workshop, and Yubo Hopkins was my summer undergrad student. Okay, so I'm going to quickly define the model of random graphs with given degrees. And then I'll introduce two commonly used tools for analyzing such random graphs, the configuration model and the switching method. Then we'll talk about some known results of probabilities of subgraphs and some new results. And in the end, I'm going to talk about how we can approximate this random graph by an easier random graph model. Okay, so random graph with given degrees. Obviously, it means that you are given the degrees of every vertex. Like in the figure shown above, I just use the number 3, means this vertex has to have degree 3, and so on. And I want to take a uniform distribution over the set of all graphs with this specified degree sequence. Of course, here we only care about the degree sequences where it's possible there exists a graph with such a degree sequence. And even though this random graph space is hard to analyze, it's still one of the most popular and well-known, most studied random graph models, especially in the field of network science, because people want to use random graphs to model the network. And over there, the graphs behaves very differently from other Schrödinger graphs because the degree sequence typically don't follow the Poisson law. And the people that care about properties such as big clusters, such as giant component, and robustness, such as connectivity, and maybe you also want to know the number of disjoint spanning trees and things like that. And for random graph people, maybe we care about typical graph parameters such as subgraphs, Hamilton cycles, clustering coefficients such as the number of triangles, and we also like to know graph parameters such as diameters, chromatic number, and so on. So I'm going to cover a little bit of these in the next few slides. Okay, so if we are going to analyze any property of such random graph, eventually everything boils down to estimating probabilities of subgraphs, or even more elementarily, just to estimate the probability that two vertices are adjacent. Well, this probability is trivial in other Schrödinger graphs because edges appear independently. But in this random graph, it's not trivial at all. In fact, for certain degree sequences, this is still open. By definition, if you want to estimate such probability, it's equal to the ratio of the number of graphs where UV is adjacent, and the set of graphs with that given degree sequence. So eventually, you can estimate this probability if you can enumerate graphs of this class. Well, in some situations, this is probably the only thing you can do so far. For instance, if D is the degree sequence where every coordinate is linear in n, and the only tool is actually is to estimate such probabilities via enumeration. But luckily, in sparse degree sequences, there are more tools and more direct way to estimate such probabilities. One is the configuration model, and the other is the switching method. So I'm first going to introduce the configuration model, and I guess most of the people in the audience probably already know it. So in this case, I'm just going to consider the class of graphs where that's 3 regular, so every vertex has degree 3. So now I'm just going to represent every vertex by a bin, and inside each bin I put in 3 points. Okay, and then I take a uniformly random matching, perfect matching over the set of points. All right, and now to go back, I just shrink these bins into vertices, and if there are 2 points that are matched by this perfect matching, this edge in the perfect matching will just be considered as an edge between those 2 vertices. Well, of course, in this way, you can potentially generate multi-edges, right? Like in this case, you have a double edge here. And it's also possible to have a loop. Nevertheless, this is in some sense quite nice because for 2 reasons. First, if you conditioning on the graph generated in simple, then it gives a uniform distribution, which means it is exactly the distribution of uniformly random 3 regular graph. If you're conditioning on that, there's no multiple edges. Okay, and the second is it's very easy to estimate the edge probabilities or probabilities of subgraphs in this configuration model. Okay, for instance, if you just look at 2 vertices UV and what's the edge probability there in this configuration model, okay, not in the graph, but well, I haven't really defined what does mean UV being adjacent, but you know, the graph terms usually translate easily into configuration terms. That just means that I have a point P1 in the bin U and a point P2 in the bin V, and then they are matched to each other. And this probability is very easy to estimate because it's just a random commutation of the set of points, right? It's a random, uniformly random matching over the set of points. So this probability is exactly 1 over m minus 1, where m is the total number of points, or in other words, the total degree of the degree sequence. And then this summation, taking the summation, this is just du, this is dv of terms. So in total, you get du times dv over m minus 1. So that's how easy it is in the configuration model. So that's there are also a few other advantages. For instance, typically, if you are studying some events in the configuration model, in the graph model, there's some corresponding concept in the configuration model, so you can easily translate between them. And if the degree sequence are nice enough, which I mean is the total degree is linear in n, and if you sum over the square of the degrees, it's also linear in n. Okay, so if both conditions satisfy, then whatever you proved in the configuration model with high probability, then it also holds with high probability in the graph model. Okay, so that's the advantage, but there's also some cons. This one thing you can see is that the translation from the configuration model to the graph model doesn't always hold. This constraint is very restrictive. It basically says you can only do such translation if you're only studying sparse graphs. And sparse here really means sparse, very sparse. The average degree is bounded. And the distributional result doesn't translate either. So it only translates results like events whose probability goes to 1 or goes to 0, and then you can translate. But if some events happens with non-trivial probability, then it doesn't translate. Okay, so that's the configuration model. Anyway, it is really this configuration model, I think, makes the early research of this random graphs very popular, and still nowadays a lot of people use this configuration model, and there are also publications based merely, I mean, they just prove results purely just for this configuration model without worrying about how you can, or if it's possible to translate to the simple graph model. The other method, the switching method, Brandon mentioned this in early morning for me, and for the rest of the audience. I think some just waked up, so you probably missed that part. So it's not bad that I just quickly review what this method is. And roughly speaking, the switching method just wants to estimate the ratio of two sets, the size of two sets, S and T. And they want to, if I have such two sets and I want to know what's the upper bound, what's the lower bound of the ratio, what you can do is, in general, you just define some relation between those two sets. And the relation, if I have an element S and an element T that are in this relation, we just call them related. Okay, and typically, why it's called switching method, we just say we can swap S to T, because in most situations, when we relate two elements, it was a situation that their symmetric difference is small. Okay, so we can swap S to T by switching some elements there. So how do I estimate the ratio over here? Assume I can count the number of elements in T that is related to any given elements S in this capital S. And I can get upper and lower bounds for this estimate. And then similarly, for any elements in T, I also count the number of elements S in S that is related to this T. And I also get upper bound and lower bound for this count. Then immediately you will get this relation. You count the total number of relations in two ways according to basically degrees from S in S and then degrees from T in T, right? And then you immediately get upper and lower bounds in two ways. And then rearranging those inequalities, you immediately get upper bounds and lower bounds for this ratio. And that's just in special cases of, according to Brandon Mckay's talk, a special case of the switching method. But this explanation is already enough for today's talk. So one thing to mention is that this method is very flexible. You can choose different kind of relations, which means different kind of switching method. And the different choices of this definition of R, it depends on the applications. And also, sometimes when you choose it more cleverly, it gives better bounds or simpler proofs when you come up with bounding some ratio like this. Okay, so now let's back to the problem that we want to estimate the probability that two vertices are adjacent in the random graph G of D. Okay, how do I do that? So I'm going to show you how I use switching method to do this. So I'm going to define S to be the set of graphs in this class where U and V are adjacent, and T is the set of graphs where U and V are not adjacent. Then, of course, the probability that U, V are adjacent is simply the size of S divided by size of S plus size of T. Well, in most applications, we actually really want to know is the probability of U, V being adjacent conditional on a set of edges being already there in your graph. Why is that? Because, for instance, if you just want to know a set of edges being present jointly, and what you can do is just do this product of this conditional probability, right? And that doesn't really change the method. I mean, the same method applies, except in the definition of S and T, you can define it in the same way, but you restrict that those graphs must contain all the edges in H. Okay. All right. So now I just want to quickly review how Mckay, in his first paper, how did he estimate such edge probability? That was in 1981. So I'm just going to fix a graph in S. Okay. And then I'm just going to, well, U and V are adjacent there. I'm just going to pick another edge X and Y in the graph, such that U and X is not adjacent, and V and Y is not adjacent. And then I do this swap. this swap doesn't change the degree sequence, but I go from a graph in the set S to a graph in the set T, right? And now, according to the switching method, I have to count the number of ways I can do this swap. Well, obviously, the trivial upper bound is basically m, the total degree. That's the number of ways I can choose this edge, x, y, ordered edge, right? I have to choose an edge, make one end x, and then the other end y. So it's upper bounded by m. The lower bound is easy to get as well. you starting from the upper bound, use inclusion exclusion. You exclude the number of choices where there's an edge here, for instance, and then you immediately get 2 times delta squared. 2 counts for an edge here or an edge here. And there are also cases where x collides with u or v and y collides with u or v. That's counting at most 4 delta. So immediately you get a lower bound, which is actually very good because these terms are much smaller than m in the sparse graphs. So the upper and lower bounds actually are very close to each other. And how about if I'm giving a graph from T, I want to count how many ways this can be produced, okay? Or in other words, how can I perform an inverse switching going from T to S? Well, I have to choose a vertex X that's adjacent to U, and then choose a vertex Y that's adjacent to V. That gives me an upper bound du times dv. How about lower bound? Well, the thing is, you can't really get absolute lower bound here because it's possible. You have to choose X and Y such that there's no edge here. But maybe all the edges you found here, all the neighbors here of U and all the neighbors of V here just form a complete bipartite graph. Then this is just 0, and it's not going to be useful for any to get any useful bounds. So what he actually did is what you really need is expected number of this count, right? So you have to do some averaging, and then eventually, if you do averaging, then you get du times dv, roughly speaking, plus some error over here. Okay, so the conditional probability here, I just make h to be empty to simplify it. So it's roughly size of s plus, so yeah, s over plus t, size of s plus t, and then that's equal to the expected way to do backwards switching and the expected number of ways to backward switching and the expected number of ways to do forward switchings. And plugging the formula from previous slide, you get this thing. Okay, and if you do the analysis carefully, this error is small and it will be absorbed by this delta square over m. So writing it more carefully, if you have an edge as a graph on the same set of vertices, and you use dh to denote the degree sequence of h, and you assume that the degree sequence of h is a most degree sequence of this d point-wise, and uv is not an edge in h, then you can estimate the probability of uv conditioning on h being a subgraph. Okay, and then it slightly changes from the previous slides because h now is not empty. So I have to subtract something here and then subtract something at the bottom. The error is the same as what's shown before. And now if you just apply this probability recursively, you can get the joint probability of h being a subgraph, and it gives you this formula. And then the error becomes delta square over m, and then you have to multiply with the size of the edge. Okay, and I just want to quickly comment that if you choose R a bit more cleverly, you can simplify the counting argument. So this was discovered later, like by Warman and Mckay in 1990, that they found that instead of using this 2-edge swap, if you do 3-edge swap, you can simplify the argument. You actually don't even need to use the averaging argument. And then several group of people actually rediscovered the proof of Brandon. I think without realizing this result has been proven before. For instance, one result was by Kim Vu Kimball and Sudakerf in 2007. They just proved this as a lemma for some other studies. And I think there are a few other papers like that as well. There are a few extension work. For instance, this one was by myself and then Van der Hofstad, Southwell, and the Sterhuis. In 2018, we extended the argument to power law graphs, where basically the condition at Mckay's paper would be violated. And also this method was generalized to random regular uniform hypergraphs by DSU's Kuhn and Delthus last year. Okay, but today I'm going to talk about a few recent improvements. One is to relax the degree constraint, delta square, that is little of m. In particular, I want to talk about how to relax it in a way that it can permit, in general, permit heavy tail degree sequences. And particularly interesting situation was that I can cope with power law sequences with exponent greater than 2, and such degree sequences won't satisfy the condition here. Let's call it the Mckay's condition. Okay, and I'm also going to talk about how you can actually translate the configuration model analysis to the random graph analysis beyond the point where direct translation is permitted, right? So in an earlier slide, I said that if a degree sequence basically if it's sparse, then you can do it. But in fact, you can do it beyond that point as well. And I'm going to talk also about how we can improve the error. The error term was delta square over m. I'm going to talk about a recent improvement on this error, and a little bit on the applications. Okay, so the new result involves a new parameter, which I call it J of D. It was not called like that when we first discovered this. So I used this parameter with Nick Wormelt a few years ago when we were studying power law graphs. And at that time, there wasn't a parameter for this, like a name for that. And later on, I realized it's actually really useful. So I started to continuously use this notation. So what it says is you just, without loss of generality, you can just assume the degree sequences are in non-increasing order. And the maximum degree, I just use big delta to denote this, and the small delta for the minimum degree. So J of D is simply the sum of the first delta largest degrees, okay, D1 plus D2 all the way to D delta. Why is this parameter important? Because it gives an upper bound for the number of 2 paths starting from any given vertex. Okay, so if I start from a vertex U, I want to know how many 2 paths are there starting from U. The degree of U is at most delta, right? And then I just sum over the degrees of the neighbors of U, which is -1. So that immediately gives me J of D minus delta is an upper bound for the number of 2 paths starting from a single vertex. And that's exactly what's needed for the switching method to work. You don't really have to, for instance, when you count the number of forward switchings, you want to use inclusion exclusion, and you want to count the number of, say, edges here, x something. That is one distance away from this U, right? There shouldn't be an edge here. So in inclusion exclusion, you want to count basically a 2 paths starting from U, right? An edge here and an edge here. Instead of using delta square, I can use J. And also another trick that was suggested by Brandon Mckay in some occasions, and it turns out to be very useful too. In the switching, usually we try to switch in a way that the vertices are all distinct, but actually just allowing x, y to be equal significantly simplifies the argument a lot. So it was a very clever idea, I think. Anyway, so if I combine those ideas together, and using same counting proof, I could write down this conditional probability of this form. Well, the thing that's different is now, instead of delta square over m, you get j d over m. And this j is obviously always upper bounded by delta square. But if your degree sequence is heavily tailed, it could be much, much better than delta square. And because we are treating with, we potentially can treat heavily tailed degree sequences, the edge probability, we may treat those cases where the edge probabilities are not vanishing. It can be some constant or even close to 1. So this probability, this formula captures that as well. And that's why you have some additional terms here. Okay. So this was the new result that I got with my student O'Hopkin. And the result itself is not really such big improvement, but what I want to tell you about something really interesting is it has very close connection to the configuration model analysis, which people typically like to use. And unfortunate thing there is, when you prove something about configuration model, there's no direct way to say something about the graph model. And what I want to say is that that's wrong. In fact, you can, and there's a lot to say. So when you try to prove something about like chromatic number or whatever, a lot of properties, typically in random graph theory, you want to bound the probability of a set of edges being present. Okay, and using this this conditional probability, you can easily write down the probability of a set of edges being present. What I want to tell now is we don't really want to get asymptotic expression for this probability. What you need is just an upper bound that is good enough. So what I care about here is just taking the product of those conditional probabilities where each term carries a 1 plus little 1 error there. So of course, when you take a lot of, if the set of edges here is big, this whole thing here, this 1 plus little 1 will build up very quickly. But still, this is actually already very good, useful bound for many applications, which I will show in the very recent slides from here. And also, I want to show that just by adding some additional very weak condition, you can show that this is actually a tight bound. It's equal. It's also a lower bound. Okay, so what kind of degree sequences satisfy this JD little of m? We've mentioned that, well, it covers Brandon's condition, and also it covers power law sequences, and a few more, which I'm not really going to enumerate here. So how do we translate analysis from the configuration model to the random graph model? I just want you to compare the probability of a set of edges that appear in this is the random configuration. Okay, I use a G star, or think about it as a random multi-graph. You somehow think about the number of ways that you can embed this set of H into matchings of the points, and then sum over all such embeddings, and then you can immediately explicitly write down this expression, and it has some form like this. And it looks familiar to you because I showed you in the previous slides that in the graph model, you have exactly the same expression, except 1 is replaced by 1 plus little 1. Okay, so that's one connection. The other is also very, very often used is in the configuration model analysis. If you have two sets, S1 and S2, they can be disjoint or they can join, doesn't matter. And often we want to bound the probability that, for instance, there are too many edges between those two sets. That means too many edges that join these two sets. Okay, and in the configuration model, this is very easy to be expressed. You choose, this is the number of ways you can choose a set of points, all points from the first set, and the number of ways to choose those number of points from the second set, and then match them. And then here's the probability of such partial matching. Well, but using the conditional edge probabilities from the graph model that we proved, you actually also get the same expression for the graph model. Again, the only difference here is this 1 is replaced by 1 plus little 1. Okay, so in fact, they are really closely connected, and I was very surprised that it was never used before and in many applications. So one of them I recently looked together with my student, Hopkins, was the chromatic number of random graphs with degree sequence D by Fries, Krivovich, and the Smiths in 2007. So what they showed is when this D satisfies some conditions, A1, A2, A3. A1 is just some kind of tail bound. A2, A3, if you work with random graphs with given degrees, you probably can immediately see why you need such conditions here, how they are imposed. So their proof method is just prove it in the configuration model, okay? And then they use switchings to switch away those multiple edges, and then use those conditions to say, okay, after you do so many switchings, the distribution doesn't change too much, and along the switching, you can control the chromatic number along the way. Okay, that's the proof. But if you actually realize the connections in the previous slide, you can immediately relax those conditions significantly. The first condition just basically goes delta is sublinear, and the second is almost the same as just degrees is sublinear. So it's very, very weak condition. And the proof is simply borrow the proof here. Just borrow the proof, actually only 30% of the proof, because I don't have to worry about switchings afterwards. I just use the analysis from the configuration model, replacing some constant there that is 1 to 1 plus little 1 doesn't change the analysis at all. So using their proof, I immediately can get a much stronger proof result with much simpler proof. So that's the first application. And the second application I looked at it was the connectivity phase transition. So I just want to characterize when this random graph is connected. It's a very, very basic problem. And I think many people in the history have studied this in the literature. The first I can trace back was by Nick Wormald in 1981. Around that time, of course, not so many models have been tools have been developed for such study. So he was doing by basically counting graphs, and degrees were restricted by, I think, bounded degree sequence. And then there are a few others. I think some were restricted to regular graphs, and some are a bit more relaxed. And the last paper was also studying connectivity phase transition, but in the configuration model only. Okay, so the one that's most comparable to what I'm going to talk about today was Wuchek's result that I'm going to just list here. So what he considered was the degree sequence where the minimum degree is at least 3 and the maximum degree at most n to the 0.01. And then for such degree sequences, you can show that this random graph is with high probability delta connected. And when delta is 2, with the same maximum degree constraint, then he also showed some kind of structural results, like when this graph will be 2 connected, when it will not be. So there's some kind of threshold. I forgot exactly if it's only one side of the threshold or 2 sides, according to number of vertices with degree 2. Okay, so here is the new result that I got recently during the lockdown, because there's not much I can do at home. Basically, it's a full characterization of the connectivity transition when the degree sequence satisfy this condition that I talk about. Okay, and it's determined by the number of vertices degree 1 and number of vertices degree 2. And case A is the regime where the random graph is connected, and case B is the regime where it's disconnected. And And case C is the critical window where you have non-trivial distribution. And the proof is simple, actually. You just really just use the connection between the configuration model and the configuration model analysis, and then basically everything. If you can do it in configuration model, you pretty much can do it in the random graph model. And yeah, I also had some result where this condition is violated, but over there it's a little more tricky, and I don't really want to talk about this today. Okay, so so the next thing I want to talk about is improving the error in this edge probability. So the error has been d over n. Here I'm just going to talk about the d regular graph to make it simpler. Okay, so du is basically d here. But h is still a given graph, so you still have a degree sequence for h. And the delta square over m reduces to d over n. And similar, j over m is also d over n. So the previous best error was d over n. And for various reasons, I feel it's really important to improve this error. For instance, if I really want to study large subgraph H, and I really want to study something more accurate rather than just having a bound. So I want asymptotic this probability, and I want to multiply them together for n times, for instance. And then that, if I multiply by n here, this is bigger over d, that's too big. So this is the work still in progress. Again, it was done during the lockdown. So what I found is that you can actually improve to, roughly speaking, d squared over n squared. And there is potential to actually improve further, but I got tired, so I stopped here. And this is a version where h is small, and when h is bigger, you can actually have another version over here where this error can be even more reduced. Okay, so roughly speaking, this is what you've seen before, and then this is some extra stuff where this is a function depending on h and u and v, which can be explicitly expressed. Looks a little messy, but if you know h, very often with some kind of manipulation, you can actually write down it a bit more nicely into this form with big O of one error in the end, capturing those various terms. And it turns out that this form is usually good enough for many applications. Moreover, this phi h is easy to compute. I'm just giving, and actually they have really nice forms. So I'm just giving you the value of this phi when h is empty, so just this particular h, and it's minus d. And if h is just one single h, and then you are talking about this u, this v, and it's minus 2d. So these I computed because I was trying to understand the distribution of triangles and then overlaps of them, and then I got to this kind of calculations. And all turns out that those functions really look pretty. Okay, so how did I improve this error? It's actually a very simple idea as well. So remember, this was what we did, this switching. I used this longer switching to get the estimate for the probability of UV with error d over n. Or in fact, you can just apply Mckay's result as well. It's equivalent for regular graph case. And the new idea is I actually go back to the simpler switching, which of course usually should be not as easy as if you're analyzing this new idea of switching. But if you already have some estimate of H probabilities over here, it's better to use the simpler one, because now I just want to estimate the expected number of ways to switch forward and then backwards. And then I can express this expectation as some function involving u, v, the h graph, and then p. P is the probability of the h probabilities I got from the previous version, which I just get, can get from previous known result that I explained, or just by Brandon Mckay's result for the deregular graph case, for instance. And then similarly for backward switching, the counts I can express as function of some function like this as well. So now what I get is this probability of UV can be expressed as some function of U, of V, of H, and the probability P. So it's like it becomes like a functional that can be expressed as a function of some functional before. That's from previous recursion. So I just run this recursion a few times, and every time that when you have a rough estimate over here, when you run this recursion, you improve the precision in the next round. It's quite really amazing. I think every time when you run, you roughly get the D over N kind of improvement. But the disadvantage is every time when you run it, the formula gets messier and messier. So I get really tired after doing just one iteration. So that's the result I presented to you. Just do it one more iteration, and then you get to the D squared over N squared. And I don't really know how much you can keep doing this. You probably need some kind of computer software to do this dirty work. But with one iteration, I can still manage to do everything by hand. Okay, and why do we want to improve such error? It turns out to be very useful. For instance, if you just want to study the distribution of small subgraphs, and here I just put a triangle here, the simplest one as an example. And now I can compute the variance, for instance, of the triangle for D up to N to the 2 over 5, and then get the limiting distribution of the triangles for D up to square root of N. It looks a little bit funny here because this is smaller than that, and you would feel, of course, getting limiting distribution should be harder than computing the variance, right? But it gives you some kind of feeling of what the variance should be if you have the limiting distribution. But in fact, it's just the intuition. It gives you some guidance. You can easily cook up some weird distributions where limiting distribution doesn't tell you anything about the variance. Okay. And then the argument easily extends to strictly balanced graphs with different ranges of D. And the previously best known result, for instance, for the triangles was by Jane Gao, who was my uncle, and Nick Wormold in 2007. For D is up to N to the 2 over 7. So this improves quite big. And again, if you can improve the error more, you can easily improve the variance. This might be a little tricky, but this you can definitely do. Okay, so that's all that I want to talk about for the subgraph part. And I really hope that people can use them to really find more applications of such results. But the second part, or the last few minutes that I would like to talk about, is how do we approximate GND or GD in general by GMP? Because GMP, the Erdős-Rényi graph, is so nice, too elegant, and so easy to analyze. So if by some sense that you can say, if some result I can prove in GMP and I can translate to GND, that would be super good, right? Because GND is too hard to analyze. And the good positive result is yes. In fact, many results we can really do it. And here is the sense of how we can approximate the random regular graph. So for now, let me just restrict to random regular graph for simplicity. So the idea is using sandwich. Okay, so I have this random regular graph, and the nice hope is that I can find Erdős-Rényi graph GMP1, where P1 is slightly smaller than D over N, while P2 is slightly greater than D over N. And then maybe now I get 3 random graphs. Maybe I can couple them together in the same probability space, such that this random D-regular graph always contains this GMP1 as a subgraph and is contained in GMP2 as a subgraph. And if this is true, then any monotone property can be translated from both sides. And this very nice idea comes from Kim Wu in 2005. And the conjecture is formulated as following. So assume D is much greater than log n, then there exists P1, P2 of the same order as D over n, and a coupling of triple random graphs such that marginally the low graph distributed as GMP1, the upper graph distributed as GMP2, and the middle graph distributed as random deregular graph, and then jointly they are coupled. So G contains GL and is contained in GU with high probability. That's a formulation. And this condition is required because 1D is smaller than log n. We know this conjecture can hold. Okay, so in the same paper, they proved that GND actually contains GMP1 as a subgraph using a coupling, but they couldn't really complete this part. And that's for the range of D up to n to the 1 over 3. And quite recently, Dudek, Fries, Rudzinski, and Silakis, they improved. Well, it's still containing only the lower part, not the upper part, and it's still the sparse case, but D now goes to lower order of n. And we completed the Kim Wu's conjecture for all D that's greater than n over square root of n, so square root of log n. So basically, if D is linear size, let's say, then Kim Wu's conjecture is true. And for D smaller than that, we also have some sandwiching, but it's not tight. So this was done previously, as in the previous slides. And what we complete is we complete this side, but with an additional log n term, roughly speaking, here. And 1D is smaller than log n. There's no conjecture, but it doesn't prevent us from sandwiching as well. You can't get tight sandwich here because there's there's a simple explanation that a tight sandwich doesn't exist. But if we allow here to be adding a factor of cube of log n, then we can still embed G and D into this GMP. And the low graph, I just put the empty graph here. You can make some small p here, but it wouldn't be much more useful than just the empty graph here. Okay. Okay, so there's a version B. Basically says that you can this same theorem over here holds also for near regular graphs, for near regular degrees. So it doesn't have to be regular. If all the degrees are asymptotically the same, then theorem A holds as well. Okay. In fact, I'm cheating a little bit here. So it holds, but the range of D changes a little bit over here in part A. But I don't want to spend time to go to those details. Okay, well, there are many applications for this sandwich theorem. For instance, all the monotone properties like Hamiltonicity and delta universal causality. I don't want to explain this. But anyway, those monotone properties, any monotone properties that you can prove with GMP, and some of them, it's almost impossible. You would think that it's almost impossible to prove directly on G and D. You can immediately translate now. And you can determine graph parameters for G and D easily by using GMP because it's sandwiched on both sides. So you can translate chromatic number, independence number, diameter, and more. And also you can even determine characterize phase transitions easily. A cool application is the following. So this was also studied by several people, bond calculation on G and D. So you take a random, say, deregular graph, and then you percolate on it. You keep every edge independently with probability P. So, okay, so you get another random graph by percolating on a random graph. And now using this sandwich result, you basically can show that any phase transition you can characterize on GMP, you can characterize on this random graph. For instance, when does a giant component appear? You can translate it here directly without any proof. Okay, so I'm just going to briefly mention how to couple two random graphs this way and the lower side. So GND, how do you embed a GMP inside the GND? What it does is you just take a sequence of edges. Okay, just sequentially, you are going to add edges into triple random graphs that I'm going to build. They start from empty graph. Okay, and then I'm always going to uniformly choose a random edge from the complete graph and then throw into those three graphs. And in the upper graph, I'm always going to accept it. And in the lower graph, I'm going to reject with a small probability. And in the middle graph, this middle graph, I want it to distribute like the random irregular graph. I'm going to accept it according to the correct conditional probability, which is conditional on the graph that has been built in the previous step. What is the probability that I can add this current edge? Okay, so the edge has to be added with a probability proportional to this conditional probability. And if I can do such kind of rejection scheme in every step, then basically this part is always going to be distributed, always have a uniform distribution, conditioning on the number of edges it receives. And the same for the lower graph. And the middle graph always going to be a correct distribution towards the building of the random irregular graph. Now I just want to choose a clever, my time over. So I want to choose the number of steps clearly in a clever way that it has the correct distribution so that these two ends, these two graphs distributed as GMP. And then I stop, and then I complete the construction of the random irregular graph. And that's why there are a few edges in here, but not in the upper graph. And that's the difficult part, right? You can't easily use this construction to complete this containment. Let me just skip a little bit. Go back to this page. So the only thing you need in this construction is this rejection probability is small. And what is this rejection probability? You want to estimate this kind of conditional probability, which was the subject we were talking about for half an hour in this talk. This is H, right? In our previous slides. So the set of edges we are conditioning on isn't too big. Then we know this conditional probability by Brandon's result, for instance. But here we have to deal with the case where H is really big and the usual switching wouldn't actually work. And I think Brandon mentioned a little bit in the morning, and I also wouldn't really have time to cover this. And I just want to briefly mention that dealing with different range of, according to how, the range of D and so on, the proof involves both the complex analysis of this n-dimensional integral and finding the saddle point and then analyze the integral in near the saddle points. That's for density. And then for the sparse case, some other case, you have to think about long switchings and also assume some pseudo-random properties of S, like such as spectral gap and so on. Brandon, I think in the morning, briefly mentioned this, and I will do the same. I'll just briefly mention this without bothering you too much. Okay, so last page. I just want to quickly mention future work, and there are actually a lot of things that can be done. More applications, because now I feel once I realize there's such a close connection between the configuration model and the graph model in terms of the analysis, there are a lot of things that people used to do for configuration model. They can all carry it to the graph phase without much trouble. And I would like to see improved error, how much you can keep improving this with this recursion. of computation. And then this would result in better distributional results for small subgraphs. And for myself, why did I try to improve the error at the first point was I wanted to study spanning subgraphs. I didn't really have time to do that yet, but that's definitely on my desk. Salvaging GND with GMP, where D is not regular or not near regular, that's also very important. Partially, I have done that already with my student, the same student of Hopkins. So those are all very interesting directions. Thank you very much for your attention. I'm sorry I used 1 more minute.
I have just a small question about your better, more precise formula for conditional probability of appearance of an H between U and V. So you mentioned that you can use it for to improve results for subgraph containment.
Mm-hmm.
And maybe I missed something, but can you use it for some more global properties that are not so local when the set of edges in the condition is bigger?
When the set of edges, can you say that part a little bit?
When the set H is bigger in the condition, I mean.
Oh, the set of H is bigger. Yes, and that's exactly why you need to improve the error.
Yeah.
Right, because when you do the product, the H, where is it? The H goes into the, so this is just one edge. If you want to keep doing this product of the conditional probability, you will have H appearing here again. And if it's D over N, for instance, the previous bound, D over N.
Yeah, but this is because
the size of H can never go to spanning, right?
I mean, can you improve results not only for subgraph containment using this more precise formula, but for some other characteristics that are not so local?
I'm not sure because this is just about the conditional probability of an edge.
Mm-hmm. Okay. Yeah. Thanks. Thank you very much for very nice talk.